Here we are.
Yeah. It's been a while.
Welcome. Yeah, we're on the air now. So welcome to Absolute Zero. I'm Rachel Bell.
And I'm Bertrand Leroy, and today, I'm very, very dark.
You're mysterious, dark, and shadowy today.
I know. Yeah, that should be better. A little better. Okay.
Very good.
Yeah, and today we're talking about the sky. We're doing a two-part series, probably the first one being why is the sky black at night, and the second one being why is the sky blue during the day.
Okay. So why is the sky black at night? I actually...
Well, first, why is that an interesting question?
Oh,
hold on. I don't know if you heard that.
Tiny dial tone.
Yeah.
The boss trying to call. Nothing important.
Yeah, the headset actually wants to make a call for some reason.
Why is it an interesting question? Well, I mean, if you are working in sciences, there's certainly reasons why it's an interesting question, but do you mean that in the sense of why is that an interesting question to average everyday person?
I don't know, both. So yeah, you might think, well, yeah, the sun is not in the sky, so there is no light except for the stars, so the sky has to be black. But if you think, for example, that the universe is infinite and has been there forever, like most people thought a while ago, then in any direction that you look, you should have a star that is in the direct line where you're looking, right? If the universe was infinite and infinitely old.
Yeah.
So you would see stars everywhere. Absolutely everywhere.
You would, yeah. Huh. That's true. And then it wouldn't be so dark.
Yeah, and you can start making calculations about what the light intensity would be, depending on the average distribution of stars and galaxies in the sky, and you would find results that would be very different from what we see.
Right. So, all right, I know why the sky is blue. I don't know that I'd be able to articulate it that well, but why it's black is I thought just simply that absence of light. But there's not really. If you look out at the night sky, it's the fact that there are stars out there. And the fact is that light does travel. It takes like 8 minutes to get to Earth. Some of it hits Earth and some of it keeps going right past Earth, right? So all stars are radiating this. So it's not like there's no light out there. There is light out there. So what's happening then? Is it the lack of air particles and stuff like that it can't refract on anything?
I'm not sure I'm following you.
So the sky is generally blue because the light hits the air particles and then it like refracts on that, correct?
We'll talk about that next week.
Okay. Yeah, I know. I'm trying like not to go off into next week's topic.
Yeah, it's a little more complicated than that. So going back to that idea about...
Was it like the absence of oxygen and air out in space, the vacuum, where it can't actually, it has nothing to refract on?
Oh,
is that
I see.
why
Yeah,
it's that
yeah.
way?
In space, the light travels pretty much in a straight line, except for a few anomalies such as gravitational wells and clouds, you know, or black holes. Yeah, yeah. So yeah, there is no atmosphere where the light can be scattered. But to get back to that idea of an infinitely old universe with an average distribution of stars, what you would see is that so the intensity of the light, like the intensity of pretty much any wave, decreases with the inverse square of the distance, right?
Okay.
because the surface of a square is proportional to the square of the radius, and it's just energy being distributed on spheres. And when the sphere goes larger, the intensity goes down as the square of the distance.
Okay.
But if you have an average distribution of stars, the number of stars in any given volume will grow also with it will grow with the cube of the radius, right?
Right.
So the farther you look, when you look farther, you get more. You get a number of stars that grows with the cube of the distance, and the intensity of each of those stars will decrease with the square of the distance. So if you integrate those two, if you integrate all the stars and their distances, what you find is that, yeah, the sky should actually be very bright if you had that distribution of stars, right?
Interesting. It would be.
Yeah.
Leave it to you to come up with math for this one. Okay.
Yeah, you can make the calculations and see what you get, what you would obtain. So we don't see a very bright sky at night, obviously.
Nope.
Which leads to the conclusion that, yeah, the universe must not be homogeneous and infinitely old. Right. So it's one more reason that's pointing in the direction of a universe that has a history and even the Big Bang. And the fact is that the farther you look in the universe, the more different things start to look. And it's actually quite dramatic. If you look only at short distances, you will see stars. If you look a little farther, you will see galaxies. You will see clusters of stars, galaxies. And then you start looking farther than that, and you see galaxies that have weird shapes that are different. So, it's like when you dig into the earth, depending on how deep you dig, you will find different kinds of fossils because they have different ages because of the accumulation of the layers.
Oh, interesting analogy.
And the sky is in layers as well.
Right. Well, that makes sense if you think about it. It may not be an organic evolution, but it's an evolution of sorts.
Yeah, you start from almost only hydrogen and helium, and then the stars light up,
star stuff,
and create more elements, and you see different stars. You see stars of different ages. You see galaxies that have just been formed, and then you see galaxies that are interacting with each other, and then you see older galaxies where the stars are older, and so on. So you can see all that stellar evolution going on just by looking at the sky. That's what's fascinating, because you don't have, well, you dig in a metaphorical way into the sky.
Right. Oh, cool. Interesting.
And if you look far enough, then you don't have stars, you don't have galaxies.
Isn't it at some point just things like nebulas and dead stars and stuff like that, right?
Yeah, you see some small irregularities, but mostly you see all dark, and that's the background.
Oh, dark.
Except that it isn't completely black. It does glow.
Ooh.
But it glows in the radio spectrum. It doesn't glow in the visible spectrum.
Oh well.
So it's black. It's black for our eyes, but it's not black to a radio telescope. And that is what we call the background radiation of the universe.
Yeah, that's how we detected the Big Bang, and by we I mean who was it? Hubble.
It's one of the most compelling pieces of evidence for the Big Bang.
Right.
Which So it comes from. I'm getting an echo of sorts here. I can hear myself speak.
I'm hearing you just fine.
Okay, good. Yeah, so what's peculiar about the background radiation is that it looks exactly like the blackbody radiation. Do you know what the blackbody radiation is?
Not really.
Okay, so if you heat up any object, the atoms and molecules are agitated by the temperature, right? And that emits light because any acceleration of any particle is going to emit some electromagnetic radiation.
Mm-hmm.
So if you make the calculation of for a specific kind of theoretical substance that is called the black body, which is something that can absorb any wavelength and then just radiates that thermal radiation, you get a very specific spectrum that has a very specific shape, and that's called the blackbody radiation. So it's what any object that you heat up will emit mostly. So if you look at coal burning, for example, you'll see a spectrum that looks like that. And this is exactly what you see. So that enables us to give that radiation the temperature that is the temperature that a black body would need to have to reproduce that exact spectrum that we are seeing in the sky in every direction.
And it's probably terribly hot in outer space.
It's actually terribly cold. It's 4
Kelvin. Okay.
But it's cold because it's been diluted by the expansion of the universe.
Oh, so at some point it was terribly hot.
At some point it was terribly hot, and which is so. This is where we talk about
same with
where
our
it
sun,
comes
right?
from.
It's terribly hot right now. Give it a few billion years, and not so much.
Yeah, but that's not exactly the same thing. So here, that radiation was actually emitted by a universe that was glowing everywhere because it was so hot and so dense. And that radiation just started going in all directions, right? And you've got all those photons flying around in all directions. And then the universe cooled down, but that radiation still had the same wavelength. That was that light was just continuing in the universe. What happened is that the universe itself expanded. So if you have a wave that is going that fast and then you expand it, you expand the space where it travels, then the wavelength itself will become larger.
To fill that.
So
kind of like water expands to fill the container that it's in.
Mm-hmm. So those waves that corresponded to a very high temperature at the time now look like they have been emitted by something very cold. And that enables us to pinpoint the exact moment when the universe started being transparent.
Okay. When was that?
I think it's. I would have to check that. I'm afraid I would say something. I think it's something like 100,000 years after the Big Bang, something like that.
Okay, so it was millions of years ago.
It's very close to the Big Bang. It's billions of years ago.
Very close. Yeah, that's really what I was getting at. If it was like more close to the Big Bang or after.
So before that moment when the universe started to be transparent and started letting the light travel large distances, the universe was so dense and so hot that the light that would be emitted at one point would hit something else very fast. So the light would constantly be emitted and reabsorbed and so on.
Okay.
And when it cooled off enough, when it was less dense, then the light started having a chance to actually travel farther than just short distances. And that light has been traveling in the universe, and we can see it now. And because it was one thing that's important to understand about the Big Bang is that it's not something that happened in a particular point. It's the whole universe that was that was smaller and had shorter distances that then expanded. So
Right.
that event of becoming transparent and those events before where the whole universe was a hot soup of plasma, that was everywhere. So when it became transparent everywhere, and that light started going in all directions from all points in the sky.
Okay.
All points in the universe. So anywhere you are in the universe, you are going to see something similar. You're going to see, no matter where you look in the sky, you're going to see that light coming in, seemingly from all directions, and very homogeneous with that same temperature everywhere.
Okay.
Without there having been any communication between the different points. That's the part that is fascinating.
Interesting. And it should continue on like that? So given this data,
yes.
Are we looking at like, all right, so end of the universe kind of theories are it might like bubble in on itself, or it just might keep going, or it might collapse?
So so there are two things here. First, will we always see that light? So the answer is yes, but we will, as the universe continues to expand and actually accelerates its expansion, that wavelength will become larger and larger. So that spectrum will seem to be colder and colder as time goes on. And at some point, it will become undetectable because it's going to be so weak and cold. And the second part of your question.
Well, there was a couple I've heard, like just over the years, various theories of how it all ends. Like we'll be around to see it, but you have the collapsing, like a collapse where it kind of bubbles in on itself, or just keeps expanding forever.
So our current understanding is that it will continue expanding, and it will expand faster and faster. It's actually accelerating.
Okay.
So it doesn't mean that the galaxies themselves will disappear like that because of that, because the galaxies have their own, they are more influenced by their own gravitation than by the expansion of the universe. But eventually, everything will become cold, and everything will decompose, and we'll have a very diluted universe with just boring stuff going on and nothing interesting, no stars, only black holes and diluted dust.
It's funny, we are the most interesting thing that we know of. Like humans, right?
That we know of, yeah.
But we might, who knows though, right? Just that we know.
Yeah.
All right, so if there's a possibility, then it's a little off topic, but if there's a possibility for multiverses, then if it's going to keep expanding, is it possible for a universe to expand right into another, kind of how galaxies collide? Or do universes just not work that way? Do they have some sort of a hard boundary? Or do I just watch too much TV?
So that's an interesting question. It depends what kind of multiverse you're talking about. There are actually different kinds, and we should do a show on the different classes of multiverses.
With a bunch of universes kind.
So, so it seems like you would be talking about something where you have one space, and inside of that space you have universes that expand into that space.
Could be.
Yeah, so there is something that kind of looks like that in the in inflation, where universes start, expanding, and they are actually part of one big space. But the thing with space-time is that it's a thing. It's not just we're not really talking about some space and time that that is eternal one.
Boundaries like that,
We are
or the opposite, that just has none.
we the space and time that we know are part of the universe. They are things themselves.
Okay.
Right. So defining something outside of those space and time notions might be meaningless.
I see. So that host universe would need some sort of space-time or something to replace it.
Yeah, and
To be able to host those other universes.
Yeah, so you might have pocket universes that are, parts of that larger space-time thing that might actually have different number of dimensions depending where you look in them. But it's a part of physics that is largely speculative at this point.
Okay.
But the important thing is to remember that space and time are probably part of the universe itself. So
Gotcha.
it's meaningless to talk about space and time outside of the universe.
Outside of it.
So seen that way, for two universes to collapse or hit each other, they would have to be part of a larger space-time, which is, there are several possibilities for that exist, and that might actually happen, and we might actually see remnants of that in the sky, depending on the kind of theory we're considering. And I think there are some of those that have been predicted and that would be verifiable, and we might actually see that happen. I don't know. It's purely speculative at this point. And there are other kinds of multiverses where those multiple universes would share nothing and would not be able to collapse in any way because they just live in different, I don't know, mathematical spaces or whatever.
Okay. So Sliders then did not have all that much science behind it.
Who?
I watch too much TV. There was an old show called Sliders in which kids would slide into other universes, and of course you get different monsters in there and all that.
Yeah, I think those shows tend to be closer to the many world interpretation of quantum mechanics. They would be closer to that sort of multiverse.
Yeah, there's no container. You just get to go slide somewhere into some other universe.
In some alternate universe, and then there is Stranger Things where you have the underworld. What was it called? The Underside or something like that. I can't remember.
Underworld?
Did you watch? Yeah, the Underworld. Did you watch Stranger Things?
Oh, I saw like the first 2 episodes and I didn't get to go back and finish it, but it looked pretty cool. Yeah, the kid got trapped in the wall, almost like The Exorcist. But was that a different universe?
No, well, it's more like a shadow universe where maybe like you have our matter and dark matter, or matter and antimatter. It's that sort of idea where you have a reflection of our world that is slightly different and scary. But I mean, it's
not like the one I live in.
it's not a science show, obviously. So yeah, the sky is not actually exactly black. It's glowing at 4K.
Nice. We just can't see it though, because our eyes are made for Middle Earth here, where there's an atmosphere and pressure against our eyeballs so that they don't pop out. Stuff like that.
Yep.
They work there. Yeah.
But it's interesting that we can actually see
that kind of stuff. That is pretty cool.
Yeah, something that happened so long ago and that is so different from what we see today.
It's neat because we get to take pictures today, but yet the pictures are of events that happen, anywhere from years to millions of years ago, that's just pretty wild, if you ask me, that we get those snapshots in time by taking snapshots today.
Yep. Oh, and another thing that's interesting about that background radiation is that there are fluctuations in it, so it's not exactly perfectly homogeneous. And the differences that you see, so when you see a zone that is actually a little slightly different temperature, this is actually a quantum fluctuation
Oh, okay.
that
Oh,
got
maybe it's a slider going into a different universe.
right. So it's that that quantum variation that just was blown out of proportion by the
Absolutely.
expansion of the universe. And you can compute exactly what it would look like for a quantum fluctuation to be blown up like that, and we see
Oh,
exactly
cool.
that. So it's
I didn't know you could do that.
one more verification of lots of things, of cosmology, quantum mechanics.
Cool.
Yep. That's it. I have nothing else to say about why the sky is black.
Okay. I don't either.
But it was an interesting mystery for people who had no idea that the Big Bang was a thing.
Right. Actually, what were the theories before this? What were people throwing out there? How about if you go back a while, go back to like Da Vinci time and stuff? Well, I bet a lot of it was rooted in mythology.
I don't know. I think that the very idea that the sky should not be black is relatively recent. I would have
Okay.
to search that, but it's probably from Laplace,
I I like
the time
those
of
little
Laplace.
interesting tidbits of what we thought something was, what we thought was true in history, you know. So that would be an interesting thing to have to look that one up for when we do the blue sky one. So
yeah, that too. So before that, I mean, yeah, we had relatively we had no idea what was actually in the sky. We didn't know that. I mean, some people suspected that stars were actually suns, but we didn't really know that.
right.
What made us realize that this was the case? Actually, probably observing the spectrum of the stars. I don't know. Something interesting to research as well. I don't remember.
I remember hearing something about somebody was watching two stars, and as one would orbit the other, or it would pull on it a little, and they could kind of see them like a star dyad. Where I don't know if I'm explaining it the right way, but they can actually see that it moved a little bit, and then they could tell. But I don't remember if that's how they could tell it was a star.
Oh yeah,
As
those
opposed
stars
to
are
a
actually
planet,
pretty frequent.
or
So
what it was. I would have to look that up too, but it's like a
well,
vague something like that's in my head. I remember reading about that.
parallax is one way that we could see that those were objects that weren't fixed on the sky, because when the Earth is on one end of its orbit or on the other end, that's a pretty big distance, and for stars that are close enough, you can actually measure
Right.
a movement of those stars in the sky, and that tells you that it's not infinitely far away or it's not fixed on the sky.
Yeah.
So yeah, but
And the
even
next
even
jump
if
would have been when we
even
went
if you
from
understand
figuring
that it's an object that is far away or that is at a finite distance, that doesn't tell you that it's a star, that it's a sun like our sun, and that it could have planets. And
right. Yep. That, and I was going to say, like, the next thing, like, to figure out, which they did, was, what's a star or planet versus a galaxy? Because often what looks like
yes,
a star to our naked eye is actually a galaxy.
well, in a telescope, they appear more like a little cloud, right? Some kind of
Yeah,
cloud.
like
So
to the
they
naked eye, it looks like
So
a star.
I think astronomers were putting those in the same category as nebulae. So which are like clouds of gas in our galaxy usually. But yeah, they were put in the same category, and I think it's only at the beginning of end of the 19th, maybe beginning of the 20th century, that we realized, no, this is actually an island universe with many stars in it, and we are in one of those, and those things are no different from what we are in, which is a galaxy.
Right.
That is a very recent discovery.
Yep.
Yep. Okay.
Still a lot of sky to plow through.
Yeah. Hubble was
He made
great.
some big leaps, yeah.
Yeah. I don't know if you remember all the photos we had before Hubble. It's hard to imagine that only a few decades ago we had
Crap. Complete crap. Yes.
Not complete crap. I mean, we had large telescopes on Earth that were pretty impressive, but Hubble changed everything. Suddenly we had lots of colors that we had never seen before, and
all kind of cool stuff.
amazing resolution. We could see stars in the process of being formed, and planets being formed around the star, and
all the good stuff.
Yep. And now we even find planets. When I was a student, we had not detected any other planets than the ones we have in the solar system. And now we have hundreds, thousands of planets.
Oh, all the time I see them finding new planets. It's not even a big event anymore. It's like, oh, another planet. It's almost like, frameworks, JavaScript frameworks or something. Like they're just coming out all the time. Nobody.
Well, yeah, there was this threshold.
It took us forever, and we weren't finding anything.
What?
There was a while and we weren't finding anything.
Yeah, because we didn't have the tools to find them, and as soon as the technology was sufficient to see them, then they're everywhere. So we started seeing them everywhere.
Yep.
So yeah. What makes the news now is when we find something that looks a little like Earth.
Yes, or if people think that they hear signals from something. I saw a couple of news headlines like that were mostly clickbait.
Yeah, we're not saying that it's aliens, but it's aliens.
Yeah, we're not saying it's aliens, but it's come click here, it's alien. No, it's not. We just got you to click on that link. Damn it. No. So,
yep.
No aliens
Yeah, that's
yet.
an interesting one. What's going on there? It's very strange. In any case, it's going to be something interesting, no matter what.
Right.
Okay.
Okay.
Cool. Well.
All right. Next week should actually be a thing too, then, because
let's do next week on Blue Sky.
Okay.
Cool. Bye, everyone.
Till later.
Yep.